Thanks for your patience. Welcome to the third lesson of Automating GIS Processes 2 this autumn term. As I already wrote in Slack, I discovered that this course has always actually been taught in 3-hour sessions. So like we're doing a bit too much for 1.5 hours, which is why everything felt so rushed last week, which is why we're gonna split, like if you compare this week's lesson with last year's lesson 3, you're gonna notice we're only doing about half of it because we also only have about half time. I hope that's okay with everybody if we reduce the amount of everything that we're teaching. If you feel you're bored in here, I can always give some extra exercise for anybody who wants to. And also all the parts that we now skip or reduce a bit are still available from either as an extra lesson, which will be published like once we're done with the course, or from last year's content. So no worries, you're not going to get bored, or you don't have to be bored. If you get bored, you can just ask me to get some extra tasks. In today's lesson, we're going to look at basically 2 different things. The one is geocoding. So that means translating addresses into coordinates or the other way around. So if you have a list of addresses and we want to know where they actually are in space, so we can carry out some GIS analysis of whatever kind, it's handy to have easy ways of translating. For example, Gustav Hallström in Gato Cox into the address of Physicum, or the coordinates of Physicum. And the second thing we're going to do is we're going to look at spatial joins, that is geometric relationships between features and between layers. So things like, is a point inside a certain polygon? All of these things are fairly easy in GeoPandas. And yeah, let's just dive in. There's still this one page which describes how geocoding works and what kind of options there are. This is not something we're going to go into detail here in the lesson, but if you're interested, read through there. We're using this GeoPy library, and that GeoPy library supports like so many public services that provide this geocoding, like translating addresses into coordinates and vice versa. And many of them are paid, some of them are free, most of them are closed source, some of them are open source. But yeah, you see there's a long list, and some of them work better in some countries, some of them work better with things that are actually addresses, some of them work better if you want to search for, I don't know, museums near Helsinki city center or something like that. Yeah, just additional reading if you're interested. But let's dive in and start with the first notebook, and that is this geocoding in GeoPandas notebook. So, as I already said, it's fairly easy to translate addresses, like well-formed addresses, into coordinates in using GeoPandas tools that are built in. Yes? Okay. Yeah, sorry. It's if you started it when I did, I made a typo here. So like I since corrected it. If you started in the last 5 minutes, then it should be correct names of folders. But right now it's the lesson 3 is not in lessons, but in lesson. Still not there. You don't have the notebooks. And within that,
I only have lessons.
And there's no lesson 3 in here. Okay. Okay, that's. Yeah, there's also an easier way. You can also go to use that Git folder here and see the repository, like if you're inside this notebooks folder. So like you first change to notebooks, then go to this Git tab, and then pull the changes, like here with the button on the top. And now it also, this is not true for me anymore, because now okay, something did not work correctly here for me either. But did it show up now? Yeah, good, great. So it's whether it's called lesson or lessons, can everybody open this geocoding file? Great, perfect. We provided here, like first of all, I'm again going to define this data directory, and you have that copy and paste it in there. So it's you just have to run the cell, and then there's this file addresses.txt that we supplied you with. It's inside this data, Helsinki addresses.txt. And it's this semicolon separated file that has like an ID column and then an address column. And we've done that so often now that I think you should do that yourself, and I'm only catching up. Can you take 2 minutes to try to load this file using pandas? And let's call the data frame addresses, for example. Start with importing pandas. Yeah. So I can slowly start to type. So if you don't have any idea, you can still, I can maybe help your memory a bit. So it's like the thing we've always used. It's this read underscore, and for pandas it's CSV usually function. And then the file name, which was in, what did I say? Helsinki addresses, and was called addresses.txt. And then there's still like a small thing missing because we're using semicolons and not commas. I'm giving you a moment to think about it yourself and figure out. Yeah, can also solve it already. So we want to say that the separator, and that's called sep in pandas, the argument is a semicolon. And then let's still see how this looks like the file. And yeah, we loaded it successfully. So we have now this data frame that has an ID and an address next to it. And we're going to use this Nomina team service today as for geocoding addresses, and maybe as a quick preview here, Nomina team is run by the OpenStreetMap Foundation, and it's powered by OpenStreetMap data, and it's free to use if you follow certain requirements, and those are like no heavy use. So you can only make one request per second, which is really not a lot. So if you think you have I don't know, an address database with like 100,000 entries, it's going to take 100,000 seconds. That's not very great. You can almost look it up by hand. But there's always possibilities of installing it locally, but we're not going to use that. And then the other requirement is that you specify this user age, and that's like some metadata that every web browser sends to web servers to tell it, like, I'm Mozilla Firefox I don't know, 102.7, or I don't know what the current version is. And this Nomina team service requires you to set that to some custom string, so they get an idea how much who or which project is using it. And we can just follow these guidelines quite easily, because GeoPandas built-in function geocode actually supplies an option to set this user agent. And it also has a built-in functionality to only query it once a second. So you have to actively override it to do it faster. And yeah, actually, like we already imported GeoPandas, I think, did we? Yes, we did. No, we didn't. Let's import GeoPandas because we're gonna need that. And then let's immediately save the result of what we're going to do in a second into a data frame, because it's got to take 1 second per row. So it would be pity if we have to repeat that a lot. So I'm just calling this geocoded addresses, and then I call this function, this built-in function, which is called in GeoPandas tools, and it's called geocode. And geocode takes a few parameters. Here is a link to the, okay, here's a link that doesn't work to the documentation. Let's search for it by hand. And yeah, it's this function geocode, and it takes one list of addresses or a series, a column of addresses, and then you still have to provide, say which provider, and our provider in that case is Nomina team that we want to use. And then you just call it, and it would return the data you want, like a point for each address if it can find it. Maybe you saw while I searched here, there's also the opposite function, which is reverse geocode, which takes a list of points and then finds the best matching address for each point. But we're going to stick with the forward geocoding. And I always have to scroll back and forth. You see it on one screen, but we have this column addresses here, which we're going to use as the list of addresses, like as the first. What was it called actually? Like, yeah, addresses. And this column addresses, and we still need to say that we want to use Nomina team, and I think it's lowercase. And I'll start that already, that comment, while you still type, because it's taking 1 second per row, and I made something wrong. Yeah, exactly. I forgot to specify the user agent, which we just talked about. And the error is, I mean, it's quite a long like trace back of the error, but the error down here, like the actual error string is really clear. So it says, if you use Nomina team, you have to use a user agent. Like you have to specify one, because that's according to the terms of use. So I would just add here still a user agent, and it's good enough to just call this, for example, AutoGIS 2022, and then it runs. And it sometimes happens that, especially if a whole classroom tries to access this, that it takes too long to respond, but we can just add like another parameter that's timeout, which is number in seconds the geocoding function waits for response before it gives up. And now it takes, of course, 4 seconds, up to 4 seconds per row. So even slower, but yeah. And it's still too slow. Don't want to speak too early. Can someone explain me? I'm not a Finn. What the lick it before it falls, what that actually means? I mean, I know what it means. Like, kind of don't speak too early, but where does it come from? Anybody? Any idea? But I don't want to lick this before it falls. So. Did it work for anybody, or do you all also get the timeouts? Maybe if we spend enough time with this, then until we reach the HSU dataset, maybe they repaired that one. Well, what? Oh, yes, now it went. Yes. So I hope it also works for all of you. Like for me, it now already created this data frame that's called geocoded addresses, and that's the return value from this Nomina team backend, from this service. And what it returns is 1 point for each address, and then like a parsed address. So if we, for example, see here, like the input address we had was Itä-Merengato 14, and then it translates it into Ruolahti 14 Itä-Merengato. So it's a bit structured in a way. And for the third one, it even knows the restaurant name. Interesting. And K-supermarket and pizzeria. Nice. But yeah, it translated all of these 33 points. Has it worked for all of you, or is someone still waiting for it?
Still going for it.
Mm.
Mine worked.
Yeah, while we're waiting, that works for everybody. Yeah, we discussed this now has a geometry column and an address, and maybe we can here also still like check, print the type of it, because this is now a full-grown geodata frame and not any more data frame. So it is really already like a geospatial vector format data set. And there's only one thing, we only have the geometry here now, and like this parsed address, but we don't have any of this input data anymore. So we don't have the ID left, and we don't have the address left. And to reattach that, we can use this normal join operation. And maybe while we wait for all of you to load that, to get back the results of the geocoding, you could revisit quickly how a data frame is joined to another one. unless you know that already. But that's from the GeoPython course from lesson 6. And actually we used apparently merge there instead of join, but it does exactly the same. So for those of you for whom this already returned a result, you can now try to join back this resulting data set with the original data set. So we want to have then all of the columns in one data frame, in one geodata frame. And I can give the hint that you want to use join, yeah, the join function of, or the join method of a geodata frame. So you want to use the geocoded addresses and I'm leaving the rest still for you to figure out. But it's surprisingly simple. Yeah, it's actually really simple. You just add the, like you just supply the input data set we had, which is, it's a data frame that has exactly the same index and the same geometry and the same shape of as our result data set. So if you just kind of run this, yeah, I not ran that already, so I have to create a new cell here to print it, but then we get like this.
So if you join two data frames and you don't specifically say on what they'll join by default, it's going to use the index.
It's going to use the index by default if you don't say how to join it. That assumes that the index is the same. So if the indices are different, actually from the top of my head, I don't know whether I would start to repeat the shorter index or whether I would just throw an error if they're just like numbers as an index. But you can have really complex indices in pandas and geopandas, so they can also be a name or also even a geometry. But yeah, we get this data set, and I hope that everybody has that now. And we need that in the next section of the exercise. So let's write it to a file, and that's like always. Yeah, still like as a note here, like if we would have done the join the other way around, like use addresses and joining in the geocoded address, then we would get a pandas data frame that has a geometry column, which is really easy to upgrade to a geodata frame again, but for the moment it would be only pandas data frame. But let's save that file for use later. So saving that into the data directory and calling it geocoded addresses. And I choose this geo package extension. And this is the error that weirdly always happens in the notebooks, but nowhere else. So. And weirdly, that was now super easy to just translate a list of addresses into a list of coordinates. The only problem was that we all 20 something people did it at the same time. So we had a bit of a, we kind of brought the server down of Nomina team, but the thing itself works like that. And there's other, if you really need to use it for a lot of rows, remember to read this geocoding overview, where there's a list of different geocoders that provide also commercial services. So for fairly little money, you can buy access to just do thousands of rows in a few seconds. But let's maybe continue with the next task of today. As the next thing, we're going to look at these point in polygon queries, which is one of these fundamental spatial geometric relationship analysis that you can do in GIS, and which you come across really often. So you want to know whether a certain point is in a certain area. And this is now called point in polygon query because that's the traditional or the historical way how it developed. At first, the idea was to find out whether a point is a polygon, but actually all of these also works for anything else. So you can also query whether a point is on a line. You can query whether a polygon is inside a polygon. So it's just the name of it is point in polygon. And the way it works is maybe if you're really interested how it technically works, you can look it up from the Wikipedia page, which is linked in here. But the idea is that you have a certain point, and then you try to find out whether you're inside or outside a polygon by running through the polygon. And if you have until you're out on the other side, and depending on how often you cross the wall, whether it's an odd or even number, you know whether you're inside or outside in the end. But let's just practically try that. All of that is again implemented in Shapely. So we could, for example, again define some simple points like we did in the very first lesson. So using Shapely geometry, so we could, for example, create now like this, like a point. And what did we use here in the example? And like this, like the coordinates are 24, 9522, and the other one is 60.1696. This is somewhere in Helsinki. And then let's also get a second point with coordinates 24.9765 and 60.1612. And just print them here so we see what they actually are. Then it all goes well. So yeah, we get two Shapely objects out of here. And let's also define a polygon. In the very same way. And maybe you remember polygon as at least one ring that's defined by at least 4 coordinates. And yeah, maybe I want to copy that, and you can copy and paste that too from over here. So we get the results we want. And let's also check out how that polygon looks like. So you can copy these definitions from the website. And well, it's almost boring because this is super easy. The points have this function, or all geometries have this function that's called, or method that's called within. And if you call that using like a second geometry, you can check whether geometry 1 is inside geometry 2. And point 1 is inside that polygon, while point 2, if I didn't make a typo, is outside. So yeah, almost too easy in a way, but that's how it works. So and we can turn that logic around too, like these all these they're called geometric predicates. They all have an inverse function, so we can also do the opposite and check whether polygon contains the point 1, and we can do the same with the point 2 also. So why do they exist in both ways? Because it depends a bit on the question you're asking. So really often you want to check a long list of points whether they're inside one polygon. So it would be it kind of semantically the question makes more sense if you ask. I don't know actually which way it makes more sense, but sometimes it just makes more sense to ask the question the one way than the other, and depending on whether you have many points or many polygons, for example, and how to formulate the question often helps with like realizing how the relationship often is, and you have both ways to figure it out, and we're gonna get to know 4 other of these predicates still today, and all of them have kind of like the inverse version. So you always have these couples of tests, and we did that now for 1 polygon and 2 points, like single geometries, but GeoPandas also allows to do that on entire geodata frames and against entire geodata frames too, so you can kind of cross them. And let's hope that, no, actually this is still not the data set that is from the WFS server that's down today, but this is a different data set. Let's try a practical example in which we checked the addresses we used, we geocoded just before, and check which district they're in the Helsinki region. So let's start with defining the data directory, and then importing this file, which is in Helsinki CD districts. There's like, you can't see that because my screen is so zoomed in, but in data Helsinki CD districts, there's this geo package that contains the suuralueet of Helsinki CD. So if we, for example, call this dataset now CD districts and import that file, then we get this list of the, I think they're this. No, they're not the Suuralueet. They're yet something bigger, but they're parts of the CD. In English, they're called CD districts. And if we maybe to get a bit of orientation how they really look like, also put them into map. Also have to use the right. Then you'll see those are like the main parts of the CD. So this one was that Keskinen, like containing Gallia, for example. And then this is Eteläinen that starts from, I think, Kruunuhakka and involves half of Töölö and then the inner city and Eira. And we want to check how many or which of our points here are inside this Eteläinen, so southern district of Helsinki. Let's also get maybe this southern district as a separate data set to make it a bit more convenient. You can skip that step or streamline that if you have a real analysis, but for now, for the exercise, let's get it separate. So I would create like a separate data frame that's called Southern District, and that would be the CD districts, but only where name is Eteläinen. And I hope all of you have keyboards in which you can type the A. Yes, good. And we do that with this location filter, or this .loc filter, which you can, by the way, leave away because it's just the square bracket does the same thing. So we filter for the rows in which this expression is true, so that the column name is Eteläinen. And that should be exactly one row. So we have now this separate geodata frame that only has one row. We can also maybe still plot that, although it's a bit boring to plot this one item, but yeah. And let's also right now again get this addresses file we just saved in the other notebook. So we can make a big plot that contains all of our input layers, so we can see how they relate to each other. So that was in if I'm not mistaken, let's see. No, apparently not. Okay. It was actually geocoded addresses that I called it. So that's the file we just produced, which has a point geometry for every address. And let's plot all of these maps into, or all of these data sets into one map. So we want to have a background with all of the districts, then the southern district maybe in a different color, and then on top of that, the points. So we see how everything relates. And in this case, all of these data sets have the same reference system, which is necessary for plots. So like the plotting functionality in GeoPandas is not so sophisticated that can reproject on the fly. But you might remember again from GeoPython lesson 7 that, yeah, it doesn't load, but I can tell you that if you want to plot multiple things into the same plot, maybe also add a title or change dimensions afterwards, you have to use this AX parameter as an input to a new plot. And the easiest way to obtain this axis thing is to just take the return value of the first plot command. You can also use these subplots, which you maybe remember from plotting like the different seasons into one plot. But it's much easier to just use the first plot. So if we say first we plot this, what did we call it, city districts. And we just save the output of that city district into a variable that we can then use to plot multiple other layers still on top of that. So we, for example, just say here this a-axis here, and because by default it would have the same color, let's also tell it should be in a different color, and the parameter for that, which is passed through to matplotlib, is face color. There's further down then a bit of an explanation in the notebook and then also in the website where you can look up what kind of parameters there are. But we could just use here face color red, for example. And if you run that, there's now 2 layers in the same plot, in the same axis, in the same figure. But let's also add the third part. And again, like use the same axis. And here, what did we change here? Yeah, also the color. So we could, let's maybe change the background color. So it's the most boring one. And leave that one then in blue. Although you can choose whichever colors you want. And let's also change the size of the dots so we see it a bit better on the projector. And we have 3 layers on top of each other. Now we can already see that there is some dots that are, some of the points are within that Ettelainen district, and many of the dots are outside. And that's the thing we wanted to find out in the first place. And again, there's this super simple method that's called within. And it's just returning a true false value again. So like a bit like what we had over here. So within a polygon, and it would say false or true. But this time, because it's GeoPandas, this method also accepts an entire data frame. And if you supply an entire data frame or a geoseries, it would try to match the first row with the first row, the second row with the second row, the third row with the third row, which now is not what we actually want. We want to check for every single point whether it's in the same polygon. So let's, instead of taking the entire southern district, let's take only the first row's polygon. So we get, so let's call it maybe southern district polygon. And yeah, I know I'm always going for these really descriptive, super long variable names, which is a bit of a style choice because it doesn't matter in these examples or in these exercises whether the variable names are really, really long because they usually still fit on the screen and they're not like 100 characters long. But in general, err on the longer side. So rather choose a longer name because then you know tomorrow again what the variable name means. Don't choose now like P equals the something because maybe even 10 minutes I wouldn't know what P exactly was. While if I now call it Southern District Polygon, I know it's what it is. So we could, and that's up here, we can choose from the first row the value in the column geometry is now the polygon itself. And yeah, it's just a polygon, and it's actually, no, it's actually a shapely geometry. And let's use that with the within function of the entire data frame. So if we now have these the addresses, and you remember that's point geometries, you can just use the it's within function, and I hope this works now. I'm not 100% sure. And ask which points are within the southern polygon. Now we actually have to use the geometry here, geometry column of the addresses. No, it's something else. Oh yeah, I mistyped this one. So it actually does work like this, yes. So we can check for each of the addresses whether it's within our polygon, and then we would get this long list of true or false. So we know the first three are inside Southern District, the fourth one apparently is not, and so on. And this list of true and false that's exactly the same length as a data frame is also called a mask because it's masking certain values. So it's kind of saying these are in, these are out. And a mask array is also exactly what we already used today. Where did I? Like here. So this is also exactly producing a mask array. So this is also producing a list of true and false. So we can use it in the very same manner. So we can again use the like the geodata frame we want to filter, and then enter here the expression that generates the mask array, like this one here, and then we get only the filtered addresses. So if I would now like do exactly that, so like use these square brackets for applying this mask array to addresses, then suddenly it's only like a very short list. The index stays the same with those points that are within the Southern District. So we've carried out the point in polygon analysis for the entire data set actually in one line. Let's still save that to geodata frame so we can use it down here. So I would say, and again, I choose this really long variable name, but feel free to choose whatever you feel right here. Actually, I'm going to do something which is super frowned upon, which is no. I'm going to use an a in the variable name, which is perfectly safe. But of course, if you give that data set to someone who doesn't have that keyboard, they're going to have a hard time repeating it. And don't do that at home. And let's now, how much time do we have? Yeah, we're good in time. Let's take 5 minutes to print, to again create a plot that has all the layers, but only the points that are within the Leinen district, so only this one here. And you can just copy and paste from what we did earlier. I'm gonna wait a bit to see whether you can do that yourself. You should be able to. It's super tiny change from copy and pasting. I bet you can. I'm gonna already copy and paste that from up here, but not implement the changes yet that we need to plot the Etelinen Southern District addresses only. So yeah, all the change that's needed is this plotting the different layer on top, and I'm also going to change the color here. And then we get this plot of the districts, this one district, and the points, the addresses that are within there. Did that work for everybody? Are there any questions? Okay, great. Then it's here. Then let's proceed maybe to the next one, which is this intersect one. It's really short notebook. And it just talks about two different predicates that are intersects and touches. And they're a bit technically defined here, like intersection means that two objects share. Okay, the boundary or the interior of one object intersects in any way with the boundary or interior of another object. So this is valid. Sounds so complicated because it's again valid for points, it's valid for lines, it's valid for polygons. So the boundary is, for example, the outline of the polygon, and the interior would be the fill of it. The boundary are the end points of a line. But everything in between, no, that's not true. If it's only one point, then it's the boundary. If it's more than one point, it's the interior. It's getting a bit complicated, but that's why it's defined that way. But usually the verbs that are chosen for these geometric predicates are really descriptive. So if two things intersect, it means that they somehow intersect. If they touch, it means that they only touch on the side. So for example, if two lines share one point, or if two geometries share like a part of an edge, or 2 points, I'm not sure whether 2 points can touch without intersecting, which is the definition of touching. But let's try it out just with 2 lines, and let's just go again with the shapely geometries. So and this time let's have simpler coordinates, so it's easier to type them. So I'm gonna have a line string that goes from 0, 0 to 1, 1. And then a second line that's going from 1, 1. And you already see here they share at least this 1 point to 0, 2. And again, like it's this really simple method of the geometry object. So just calling asking does line 1 intersect with line 2 is using this intersects method, and running it says true, which they do in this like 0.1.1. But do they also touch? It's exactly the same, like, yeah, it's true. And then if you have multiple shapely geometry objects, to plot them in the same drawing here quickly, in like if I would now say like separately, like line 1 would be plotted like this, but it's really hard to add line 2 into the same plot. But it would not plot them then, because it would rather print the tuple. But there's a really handy shortcut here, which is we can just add them to a geometry collection, which technically is a new geometry, but then this new geometry is being plotted here. And I think the line 1 is the one that goes from 0, 0 to 1, 1, and then the line 2 goes from 1, 1 to 0, 2. And you can see how they relate to each other, and they meet in this 0.11. And this is now a bit of a silly example, also because it involves me saying line 1 touches itself, but also like for other reasons, it's a silly example, because comparing a line to itself is a bit of a complicated thought experiment. Let's assume there's a line 1, and then there's another line that just happens to be exactly the same, because line 1 would intersect with itself, because it does share some of the points. In fact, it shares all of the points. But to illustrate the difference between touching and intersecting is line 1 does not touch itself, because it shares more than just like the boundary or just an edge. So it shares like it shares all of it, but it shares more. It shares also exterior parts. This was all on this intersection thing. It was mostly to illustrate that within and contains are one kind of geometric predicate, but then there's also intersects and touches, and there's still a few more. And actually, there's links here on these descriptions of intersects and touches, and you can see here in Shapely there's many more of these predicates defined, or many more, some more. So there's also equals, almost equals, contains, we had that before, covers, is covered by, crosses, is disjoint, intersects, overlaps, touches, or within. So yeah, so we've seen a few of those, but there's a few more, and they're all here described in very technical language, but the verb itself already tells actually quite a lot about how they work. Also, if we proceed to the next notebook, there's in the very beginning a link here from the PyGIS book. There's really cool drawings of how this actually works. So, for example, the crosses predicate only works between lines and lines, or polygons and lines, or lines and polygons, because crossing kind of the verb crosses already kind of implies that there's some linear feature. Intersecting can work with anything, overlapping again can work only with like parts of the different geometry types. Touching apparently works with all of them, and within, yeah. Anyway, like there's a long list explaining the different kinds of predicates there are, and I wonder whether all of you already opened this notebook also, the spatial join notebook, because there's also this list of predicates that GeoPandas supports. So it's not all of these that we just went through, but just a subset. And I think all of them are logical for now. And yeah, what this whole notebook about is about is that if you have two entire layers and want to combine them, and not only one layer and one single feature, you want to, for example, know what is the postcode of the district that a layer of points is inside. Then you can use a postcode polygon layer and query for all the points in your addresses database, where they would into which polygon they would come to lie inside. We're going to use that right now in a slightly different example if the HOSU WFS endpoint works. On top of that, we still need to know that joining two data layers, we just did the super easy one where both data frame were the same size and the same index. So that's super straightforward. But if they're different and they're joined, for example, now with what you're going to do in a moment, using a geometry relationship between the two databases, then you have to decide what to keep. So Pandas geodata frames only support one geometry per table as of now, easily. So you have to decide which geometry to keep, and also if there's no match for all values, for example, of one table in the other table, do you want to keep the left or the right table? So these kind of you have to decide. And this decision is called the join type, and GeoPandas implements only 3 different ones of these here. And do I have that open still somewhere? No. Yes, I do. Because also this PyGIS book explains quite well how these join types work. So if we have a left and a right data set and we join them together, if we have an inner join, it means only the part that's available in both databases would be retained. If you have a left table, that means every record of the left side will be retained, but those that from the right hand data table that don't have a match in the left one will be discarded, and vice versa. And GeoPandas does not implement the outer join, which would be like, this is actually a bit of a misleading drawing, because it might be that there's not even an overlap in here for all of the records, and it would still keep all of the records of both sides. But yeah, let's try whether this dataset works. Of the HOSU. So we want to try as an example here to use these addresses and find out what is the population density at that address, or in the population grid from a population grid dataset that contains this specific address. So first we need to load the addresses that you just saved before, or actually I did call this geocoded addresses. And then let's see whether this dataset from the WFS endpoint works already again. Yeah, and I think it does not work. Yeah, this Geo server run by OSU apparently broke this morning. I have an alternative. Because this really doesn't seem to work. The alternative is like a shape file from also from an internet address. Also, it's also from the Helsinki region InfoShare. And it's a very long string, and I'm sorry you have to type those now and can't copy them from anywhere.
Like paste it on Slack or something.
Yeah, I could do that. That's a good idea. Great. I'm gonna remove this one cell that didn't work. And what you can see here also is like this very long string I typed in here. I just divided it into two strings that are underneath each other, and because they're within parentheses, Python just puts them back together. So like you don't like it's this here is equivalent to if I would have used a plus in between, but because there's an opening and a closing parenthesis around them, it works just like this. But yeah, we have this population grid, and it's a grid overall of Helsinki region, metropolitan region, and it has like many columns here, which are apparently in this row, like no data values because there's probably too few people. But the interesting part here is the asukkaita, which is the population, the number of inhabitants, and then over here, which I can't show you now because it's almost at the side of the screen, there's a geometry column that has a polygon, and these polygons refer to 250 times 250 meter cells all over Helsinki. And let's kick everything except for the asukkaita and the geometry, because we're not really interested in these age groups for now. So I would, what did I call this now? Population underscore grid, yes. So, and also covered that in GeoPython, but to filter for an like kind of to filter into only like a subset of columns, you can use this again square brackets, but then inside the square brackets a list of the column names. And we want to keep geometry because we need that for the analysis, and then let's keep asukkaita. So that's kind of reducing the population grid if we still show that another time here too, that it only has those two columns. And because this is an English language course, let's also rename the column here. And we had that last week, like we can use like how to rename columns, and you probably remember that it's simply passing in like a dictionary with the original names as the keys and the new names as the values. And that would give us this data frame that has one column called population and one column called geometry. Now we were interested in the population density, and population density is usually measured in people per square kilometer. And so if we assume, because this looks very much like these long values as if this reference system would be meters, but let's double check maybe. We can show the population grids CRS here quickly to double check that the values used are indeed meters, which they are. That means if we calculate the area of a geometry, it's going to be in square meters, and this now, yeah, million square meters as 1 square kilometer. If you remember, from, I don't know, high school physics or high school mathematics, so we could now easily add a new column here to this population grid data set that's called population density. And its value is supposed to be the population grid number of population, number of inhabitants, divided by its area, except that this area is 9 square meters. So we have to still divide that area by 1 million, like 1 million to end up in square kilometers. And this is explained down here. I use this underscore here now to make it easier to read this number. So you can use underscores in any numeric value in Python, and that can be decimal, that can be hexadecimal, that can be binary. It would be discarded, it would show in the code, so you can easily read that you now specified like 1 million, like two groups of 1,000. But it would still be interpreted as a number. And yeah, typo over here. And that would give me the another column with the population density. There's another tip in here which doesn't apply now the way I wrote it, but if this, because this line is very long, so it's kind of good, it's good style to break it into multiple lines, and you can always use this parentheses for it, because then it's easier to read it also if you're really zoomed in or if you have a small screen. So if I would have written it like this, there's another style convention that says that mathematical operators or operators in general should be on the new line. So they should not be up here, but rather down here. And the reason is that it's easier to see on the new line what you're doing and then which operation you're carrying out. So it's a convention, but it really, those are things that once you've internalized them and do them automatically, it helps a lot to read your own code in a week from now, because it's much easier to see in the beginning of the line that now you're dividing and not you have a new value and then you have to search where does the other line end and how to do that. But anyway, so that's exactly the same that we talked before. And we only have 5 minutes left. Really quickly, we talked about that before. To carry out these spatial join or these geometric operations, you have to make sure that input layers have the same reference system. So you can use again this assert statement for that. And apparently it's not true. So if I didn't add an error message here, but apparently they don't share the same reference system. But we can simply reproject them to each other. So if I now say that I would transform the population grid, I can just pass into here like the definition of the reference system of the addresses. And of course, I want to also save it back. And if I now run this one another time down here, then it's true. So finally, we can do the joining on the entire table. And we need for that the predicate. So which one should we use if we want to know that where the points are within, oh no, now I gave it away. Where the population grids contain the addresses. Yeah. I asked wrongly because it's too obvious that it's within or contained, depending on which way you ask it. So if we now say we add to the addresses the population information, we can just use this s-join, and this is now the most important function of today. So this is joining to GeoPandas data frames by spatial relationship. And we want to join it with the population grid. That's exactly the same as with like the normal join one. But then we have to say what we want to use to join them. So we specify predicate. And in this case, it's within. And we want to keep the left part. And the left part in this expression is literally the left one. So like the first one we wrote. So like we wrote the addresses first. This is the left one. This is the right data set. And we want to keep all records of the left side and discard, and also the geometries of the left side, and discard the stuff that comes from here, except when it matches. And if we run this, join it and then print it, then you can see how we now have a data set that has the original addresses and the point geometry, and then the population density of this particular 250 meter times 250 meter grid cell attached. There's still something really interesting on the website. Maybe let's see it from there, which is styling map data. And it would be good if you read that at home, because you need that for the home exercise, but we don't have enough time to really walk through it anymore. The thing is, like, if you run plot and specify a column, that means that this column decides how the map is styled, and it's decided also according to the color map, C map, that you pass in as a parameter, and there's links here explaining how they work, and also which categorization scheme. So that's a bit like in a desktop GIS, you can choose via, I don't know, pretty values, pretty breaks, or quantiles, or equal number of equal interval. And if you use legend, you can print a legend here. So so you can use that to then style the points according to the population density at their address. And you can also use that to style the entire population grid data set. But now still maybe quickly for the exercise for this week, it's also a bit less than last week's exercise. But it consists of 3 different problem sets, and I'm opening all of them already. They all work with geocode and spatial join. So the overall aim of all problems together is to find out how many people live within all the grid cells that are within 1 kilometer of shopping centers. And we have a list of shopping centers here. And the first task is to find their addresses from, say, the internet, and create a new text file to then read in and geocode. So that's the first task. The second task is load this list of shopping centers that you just created, and create buffers around them. And there's a good description here of what buffers are if you're unsure and how it works, but it's again like this super easy, just saying buffer and it creates a buffer. That's all of the problem 2. And then problem 3 is loading this population grid, and let's hope the HOSU dataset is working again in the upcoming days. If not, we're going to figure something else out. And then finding how many of these population grid cells are within this 1.5 kilometer buffer around each shopping center, and then in the end printing these kind of assessments of X people live within 1.5 kilometer from Tripler Redi Forum. Yeah, there is, in contrast to the previous exercises, there's not going to be this automatic grading, because I noticed that a few of you got a bit hooked on it, and I think that's maybe a bit unhealthy. If you sit on Sunday midnight and try to get this half point that you're still missing, I thought it's maybe better if we try now for 1 week to only give you the grade afterwards. There is all these test cells in the middle here, which you can use to check whether you're on the right path. But yeah, don't spend your Sunday or Saturday nights doing homework, please. Are there still any other questions? No. Okay, thank you. It still got a rush, even though we had so much less, only half of the lesson. But I think it still felt less rushed than last time, and I hope you also are less overwhelmed with the amount of stuff I now put on here. Have fun doing the exercises. Come to the Friday work sessions, and use Slack to ask questions if something doesn't work. Thank you.